Hello everyone, this video is about a class project in machine learning of HKUST Spring semester. We are very glad to present our project about a CycleGAN experiment in Cat2Dog transform. First, let me give you a brief introduction. So CNN has gained a lot of attention recently in many fields by the good performance in image feature extraction. So pixel to pixel and CycleGAN are two very famous architectures in image style transfer, while pixel to pixel still need paired data and CycleGAN breaks the limitation. So our target is to build a model based on CycleGAN to achieve cat-to-dog transfer. The dataset includes 7,000 cat-to-dog images. After we got the model, we do some experiment like GIF transfer or video transfer. And the result we get shows that images with certain pattern will show the best result, while there is also some failure examples. Generative adversarial network is an architecture that includes two nets. One is called generator and the other is called discriminator. Generator generates images from random noise, while discriminator's mission is to tell the real image and fake image apart. So as the time goes on, the fake image that generated by generator will be more and more like the distribution of real image. So the difference of pixel to pixel is the input of generator is not a random noise vector but an image. So it's learning the map from a given image to achieve the goal that can transfer the image style A to image style B. CycleGAN, it learned the map between unpaired data because it believed there is some latent pattern of the two data set, and it also added a cycle loss to the whole architecture to avoid the situation that they will map all data to one, and so that the model will break down.
Now let's take a look at the network structures we are going to use for our project. Firstly, the basic CycleGAN structure. The basic CycleGAN structure consists of two types of models, namely the generators and the discriminators. The generators are responsible for transforming an image from one set to another, and the discriminator's job is to tell if the image belongs to that set or if it's just a random image. First, let's take a look at the generators. The generators consist of three different phases: encoding, transformation, and decoding. During the encoding phase, the input image goes through a series of convolution layers to extract lower layer features. Afterwards, resonant blocks are used during the transformation phase to extract further information. The output size of the transformation phase is the same as the input size. It will reserve some original information of the image with the help of short links. Finally, deconvolution layers are used to restore an output image the same size as the input image. This whole process could be viewed as an encoder-decoder model. As for the discriminators, it applies the methodology of the so-called patch gun, which generates an output after some convolution layers. Each element in the output is responsible for determining the validity of one patch of the input. There are some certain alterations we're going to propose on both generators and discriminators to strengthen its possibility to convert an image from one set of cats to one set of dogs. Firstly, for the generators, we're going to use the UNet, which is used in the pixel-to-pixel model. The difference between UNet and the original proposal in CycleGAN papers is that the UNet will downsample the input image all the way down to 1 times 1, and there is no transformation phase. We would like to investigate the reasons behind this structure being abandoned, with the fact that pixel-to-pixel and CycleGAN are proposed by the same group of authors. And for the discriminators, inspired by some analysis, the original discriminator's patch size is too small and that a small region of a cat and a dog may not be so distinguishable, and thus making the shape changing process somewhat infeasible. Therefore, we would like to propose a more global focused discriminator to help us tell two object sets apart. In the implementation, we apply two different scales of discriminators simultaneously with different weights assigned. Therefore, altogether 4 discriminators are going to be trained, with 1 generator targets by each 2 of them. And this leads us to the loss function. As the 2 models, namely the generators and discriminators, are trained separately, so the loss functions for them are also separately proposed. Firstly, for the discriminators. An iteration of this type of loss function would be binary cross-entropy loss after taking an average of the output tensors. However, as the original writers of the paper CycleGAN proposed that using a simple mean square loss instead of the binary cross-entropy loss would perform better for the model. Therefore, we will adopt the findings of the writers. And the 4 discriminators are going to be trained separately using their separate loss functions. As for the generators, things will be a lot more complicated. Firstly, the generators will use 4 different losses to combine a loss function. The first 2 losses are simple discriminator loss, and the third one is called cycle loss. Cycle loss is the core of CycleGAN. It is proposed as follows. An image from set A is supposedly to stay the same after it is transformed using the generator A to B and followed by the generator B to A. Same for the image from set B. Later, we will compare the L1 distance between the original image and the so-called reconstructed image. And we will add up the 2 losses from set A and set B and therefore get the cycle loss. The fourth one is called identity loss. The intuition is that, for example, generator A to B should be able to distinguish images from set B and make no alteration on them. This is done by applying an input image from set A to generate A to B and check the L1 loss between the output and the input image. This loss will help preserve some higher layer data like color and shapes. To put the 4 losses together, we're gonna apply different weights on each separate loss functions. And by adding them up, we will get the ultimate generator loss.
Now I will introduce the datasets in our experiment. We use 3 datasets in the experiment: Host Zebra, Celeb A, and Cat2Dog. Host Zebra and Celeb A are regarded as baseline to ensure that our model is correct. Cat2Dog is the dataset we mainly test on, containing more than 10,000 images of cats and dogs crawled from the internet. Since Cat2Dog is crawled from the internet, there exist many noises and low-quality images. For better training efficiency, we manually clean the noises and low-quality images to maintain a high-quality dataset that fits our experiment. In order to obtain a more robust model, we randomly apply image flopping and cropping to artificially increasing the complexity of training set. After preprocessing, we set the input size of images as 256 by 256 by 3.
And now for the implementation details. We used Keras API and TensorFlow backend for our implementation of the model. After implementing the models, we also wrote scripts for training and testing procedures with configuration as input parameters. This way, it will be easy for us to compare the different hyperparameters. The details of them will be listed in the final report. And after a series of experiments on hyperparameters, we have found the following training parameters as the best for our goal of transforming cats to dogs and vice versa. Firstly, we found that using UNet as a base network for generators performs poorly, as it will result in a slow convergence, even on simple transformation dataset like horse to zebra. And also, identity loss is not so helpful in terms of shape morphing, as it tends to preserve higher layer features like colors and patterns, and slows down the potential morphing process. On the bright side, however, the multi-discriminator strategy works, and the both weights for the two discriminators are set to 0.5. Cycle loss deduction is also helpful for accelerating the morphing process and frees the model from simply getting accustomed to invert the color. The original weight for cycle loss is 10, and the final weight we use is 3. Learning rate and learning rate deduction strategy from the original paper still works and solves the problem acceptably in terms of speed and quality. We will continuously use 10 to the power of -4 as the initial learning rate, and linearly reduce it to 0 after 100 epochs, during another period of 100 epochs. For each epoch, there are 3,000 steps, which means we will randomly choose 3,000 images of cats and 3,000 images of dogs for each epoch. And the batch size we're going to use is 1.
After setting all training parameters, we train the model on the baseline dataset first. From the result images, we can see that our model is generally correct. Then we train and test on the Cat2Dog dataset. Look at the results, we get acceptable conversion and reconstruction. After conversion, dog obtain some features of cats like small nose and soft texture. Meanwhile, cats get black nose and long face. Using the model, we also apply conversion on GIF images and videos. The GIF conversion is shown as this. The video conversion is shown as this.
Let's analyze how the model learns to do transformation between cats and dogs. First, let's have a look of some examples from training process. In the beginning, the model starts to alter the texture and colors of target's fur. About 60 epochs, the shape morphing started to take place. In this picture, you can see there are some small changes on their organs. After 150 epochs, the conversion is much better, but there are still some failure examples, like these two. During our test, we found some interesting phenomena. If we want to achieve better performance of one image, we can zoom in the target. This is the original one. After zoom in, the outcome is improved. Besides, if the improved image is a cat or dog with brown fur, the result tends to be better. Because in our datasets, the number of cats and dogs with brown fur is larger than those with other colors. Here are some good examples. Finally, let me draw a conclusion of what we have done. During this project, we trained a CycleGAN model to achieve cat-dog transfer. Firstly, we reproduce the original paper to ensure our implementation being correct. Then, we use the datasets of cats and dogs to train the model. And we conduct alterations and experiments to improve performance. After that, we do GIF and video conversion to show some simple applications of cat-dog transfer. Finally, we analyze the phenomena showing up during the text process. With the introduction of CycleGAN, Various other methods of image-to-image translation were put forward. One of them that caught our eyes is multimodal unsupervised image-to-image translation. This will be our next step into this aspect of research. That's all, thank you.